All right, well, thank you very much to Nicholas for putting on this fantastic conference. This is my third time at Multicore World, and it is now a fixture in my calendar. I really enjoy coming here and seeing some familiar faces and also meeting some new faces. I think it's just a wonderful collection of people. So today I'm going to talk about some of the work that we've been doing in digital twins. In terms of my one slide of introduction, rather than introducing myself, which you can read about me in my bio if you like, thought I would just say a word about the Odin Institute. Many people here probably are familiar with the Odin Institute, some of you may not be. So we're a really unique and fantastic interdisciplinary research focused on computational science and engineering. We're at the University of Texas at Austin. We're a sister institute to TAC. So while Dan has got the supercomputers and a lot of the people around sort of the high-performance computing, the Odin Institute is really focused on the computational science. So we bring together about 140 faculty members from 26 different departments across campus. We bring together math, computer science, the natural sciences, so physics, chemistry, biology, all of the engineering school, the medical school, more recently the College of Pharmacy has started to engage with us, the Jackson School of Geosciences. So we have a very, very broad connect all the way from the foundational mathematical, statistical, and computer science research through the applications across a range of areas. Really fantastic place to be if you are interested in work at the interfaces of modeling, computing, and applications in the physical and natural and engineered world. All right, so let me get started on the talk about digital twins. And I have to say, Nicholas, this thing's going to drive me crazy, but that's all right. I will try not to fiddle with it, and I'll try not to move too much. All right, so just starting off with the question of what is a digital twin. I was very privileged to lead a nationwide study that I talked a little bit about at Multicore World last year on foundational research gaps and future directions for digital twins. This was a study done under the auspices of the National Academies of Science, Engineering, and Medicine in the United States. And one of the things that study did was to put forward this definition. Digital twin is a set of virtual information constructs that mimics the structure, context, and behavior of a natural, engineered, or social system or system of systems, is dynamically updated with data from its physical twin, has a predictive capability, and informs decisions that realize value. The bidirectional interaction between the virtual and the physical is central to the digital twin. So there's a lot of words there, and this graphic, also from the report, really sort of captures the essential pieces of that definition of a digital twin, and really emphasizes a couple things. First, that a digital twin is really a paradigm for us thinking about integrating data, models, and decisions. And second, that a digital twin, yes, builds on the simulation and modeling that many of us have been familiar with over the past decades, but really goes beyond being just simulation and modeling. And so in this figure, we see here the physical counterpart, which could be an aircraft, a spacecraft, could be a human, could be a patient, could be a farm, could be something in the natural world. We see over here its virtual representation. So here is the modeling and simulation, whether it's physics-based mechanistic models or your favorite machine learning type models or statistical models, empirical models, all the different kinds of ways we virtually represent a system. But then what we see is that the digital twin is more than just this piece. This bidirectional flow from physical to virtual and virtual to physical, again, going back to the definition, are really integral to the notion of a digital twin. So the flow from physical to virtual, this is where we take observations of the physical counterpart, whether it's sensors on board an engineering system or maybe remote observations of something in the natural world. And through the process of solving an inverse problem or doing data assimilation, we are assimilating or incorporating those observations into the virtual representation so that that virtual representation is being updated to reflect this particular physical counterpart and also to dynamically follow the behavior of the physical counterpart as it changes. Then on the flow from virtual to physical, this is where we're now taking this personalized, dynamically evolving virtual representation and using it to effect change in the real world, either through control or some kind of decision making, making decisions about treatment for a patient, or also through making changes to the observations. So deciding to deploy a new sensor, maybe drill a new ice core in an Antarctic ice sheet, or in the example we saw yesterday, deciding to fly your drones in different ways to collect observations, or maybe in the medical setting, deciding to go for another test or another image. And this, these bidirectional flows, this is sort of a continual back and forth, continually affecting change in the physical world. The physical counterpart is changing. The data are collected, observed, assimilated. The virtual representation is updated. And again, we have this continual back and forth. What you notice is in the middle of it all are potentially humans. Yes, there are many or some applications of digital twins where we may be looking at fully automated or fully autonomous control. But there are probably many more applications of digital twins where there will be a human in the midst of it all. And so thinking about how humans interact with digital twins and human-in-the-loop decision-making is a really important piece. And then finally, I'll draw your attention to the arrows around the outside, where we have topics like verification, validation, uncertainty quantification, security, privacy, and ethics, which are all particular challenges as we move to this paradigm of this sort of deeply coupled setup between our modeling simulation and our physical counterpart. So, again, that's just a little bit of framing. This is the way that we think about a digital twin with all these different elements. And as I go on to the technical part of the talk, I'll sort of refer back to this because one of the challenges that we have, and what I'll talk about today, is just the complexity, managing the complexity of all of this, particularly as we try to build digital twins of physical counterparts, where we're bringing together many different pieces of models and different sources of data. So what I'm going to discuss today are two things. One is I want to tell you a little bit about the way we use graphical formulations in my research group as a way to really architect or to sort of abstract and then build a mathematical foundation for thinking about digital twins. And then the second one, I want to show you a little bit of the work that we've been doing in building an educational digital twin. I almost never get to talk about this stuff. This is like a side interest for me because the vast majority of my work is in aerospace engineering and energy applications, and I'm usually going to engineering conferences, and so I hardly ever get to talk about the educational work. And I think because we have such a wonderful, diverse audience here, I was really excited to show some of that. Do want to acknowledge the support, a lot of the graph work and the foundation supported by the US Department of Energy, the educational work supported by the Texas Higher Education Coordinating Board. All right, so let's start off with this idea of using a graphical formulation to represent a digital twin. So I have here up on the slide a quote that comes from Michael Jordan's book, Learning in Graphical Models, which I think was published in 1999. Graphical models, a marriage between probability theory and graph theory, provide a natural tool for dealing with two problems that occur throughout applied math and engineering, uncertainty and complexity. Fundamental to the idea of a graphical model is the notion of modularity. A complex system is built by combining simpler parts. Probability theory serves as the glue whereby the parts are combined, ensuring that the system as a whole is consistent and providing ways to interface models with models to data. So I love this quote because Michael Jordan, who of course is a giant in the field, could have been writing about digital twins, but the term digital twin had not even been coined at the time he wrote this book. So I put the quote here because I think it really emphasizes that as we start to think about building digital twins, and especially for many of us, where the digital twin is building on top of modeling and simulation, which means that we're starting with our favorite PDE discretization simulation tool, finite element, finite difference code, starting from there and trying to couple in the data and the decision making, to recognize that there are other ways to think about architecting a complex system that's going to be built by combining a lot of different pieces, and that graph theory really provides a foundation for doing that. What's really essential about graphical models, and maybe what's a little different, is that in a graph model where you have nodes and you have edges, the edges represent the relationships, and the relationships are just as important as the nodes, as the entities. So the fact that a graphical model emphasizes a relationship, I think, is absolutely key to this idea that a digital twin is more than just plugging a few more things into a more traditional simulation and modeling approach. So with this idea that graphical approaches could provide a way to address complexity and uncertainty, which are maybe two of the biggest challenges, and I shouldn't say biggest, two very, very big challenges in digital twins, what would that mean? So what we have been working on is a multi-layered graphical formulation, again addressing these two questions of complexity and uncertainty quantification. And without diving into too many of the gory details, I'm going to give you a sense of how we do this. We're really doing it with two layers. We have a bottom layer that we call a foundational layer, where we use a knowledge graph. And this is, by the way, the part of the problem that most engineers and computational scientists like me just skip over, because by the time we get to the problem, it's already a very well-defined problem statement. But of course, the real world is not like that. So I'll show you how we use knowledge graphs, a field that has just progressed by leaps and bounds in recent years, to provide this way to the semantics for the digital twin. And then we have what we call the predictive layer, where we use probabilistic graphical models as a way, again, to architect the digital twin. And that's really a key construct, because this is where we can now inject uncertainty quantification into all aspects of the digital twin. And then I really won't talk about it today explicitly, but I really do want to emphasize that even though we are using these graphical constructs to represent the digital twin, all of the partial differential equation-based methods, the discretization, the optimization algorithms, the Bayesian inverse problems, your favorite method for solving an optimal control problem, whether it's dynamic programming, now called reinforcement learning, or some more classical approach, all of those methods still sit here. They sit on top of our graphical formulation. So we're not replacing those, I hate to call them classical, but those other approaches that we use. All of those approaches are buried in here, but they are done in such a way that they're consistent with this graph representation. Okay, so let me say a few words about the foundational layer. I probably don't have to emphasize to this audience just how complex. I mean, pick your favorite system, and whether it's an airplane or, I don't know, an oil reservoir or a farm or a bridge or a building, pick your favorite system that you want to build a digital twin of, and just start thinking about all the pieces that you would want to include in the digital twin if you were really going to have this living computational model that would drive the very best decisions. So how to manage that complexity, how to deal with the fact that you have potentially so many different sources of data that come in different shapes and sizes, not to mention different formats, maybe different scales in space, different temporal frequencies, all over the map. That you potentially have dense interconnectivity, where this sort of bidirectional interaction between the digital and the physical world, and you think about all the information that could be flowing along that. There could be a lot going on. And then just the whole challenge of how do you manage errors? I mean, how will you know when a sensor is giving you an anomalous reading? How do you know when you have pieced together all these different parts of the system and then introduce things that just don't make sense because you made a mistake or because you've got so many groups involved? So there's just so much complexity in terms of architecting. So as I mentioned, we use a knowledge graph as that foundational layer. What is a knowledge graph? It's a mathematical structure. It formalizes the semantic knowledge that you have and organizes it, and then provides kind of a platform on what we can think about doing scalable computations and bidirectional data flow. So let me show you this as an example, and I know the text and the nodes may be just a little too small to read, but this is an example of what a knowledge graph, building a knowledge graph for a digital twin of an unmanned aerial vehicle. So a lot of the work that I've done in digital twins over the past decade or so have been around building digital twins for structural health monitoring of unmanned aerial vehicles. And here's an example of an ontology where we would define the idea we have models, we have sensors, we have components, we have control actions, we have quantities of interest, we have parameters that we want to track, and the knowledge graph defines all of these different entities, all the different kinds of things I can have in the system, with the edges defining the relationships between the different parts of a system. So a sensor generates a measurement, a model assimilates a measurement, a model is parameterized by a parameter, all the relationships in the system. Of course, in the knowledge graph, we can also specify different properties for each one of the entities and each one of the relationships. Then on top of building this sort of ontology, this general ontology, we can then start to create a knowledge graph. Here, an example of an instantiation where we might have a structural model, and one of the cases that we've considered with this unmanned aerial vehicle is, could the digital twin, the structural digital twin, be assimilating data from the sensors on board the aircraft while it's flying, so that if the aircraft were to get damaged, the digital twin could do real-time updating and then replanning of this aircraft, or this unmanned aircraft, so that it could fly safely. And again, this is just an example, but showing you how you could go from this general ontology to a particular knowledge graph that, again, is just articulating all the different pieces of the structural digital twin for the UAV, and how things like the left aileron, which is one of the controls that you have on the wing of this aircraft, how that is connected either directly or through these pathways to all the other pieces that are invoked in the digital twin. So of course there's models, data, and decisions already encoded in this knowledge graph. Once you have all of this formalized as a graph, you can then start to, of course, use all the tools that become available to you as a graph, and so doing things like looking for illegal cycles. Can I have a tail that contains a vertical stabilizer, which contains a rudder, which contains a control system, which contains a tail? No. So having the power to do these kinds of things is really what is going to let us move beyond having to build the digital twin one system at a time with a whole lot of human and manual checking, but actually get to building things in scalable ways where we can start to deploy the power of in this case, knowledge graphs and the kinds of automated actions that could be carried out to query different aspects and structures of the graph. Okay, so that's just sort of a little high-level look at the foundational layer. Let me talk now just a little bit about the predictive layer. So remember I said for the predictive layer, this is where we really want to make sure that we are incorporating uncertainty. I firmly believe that constructing and deploying deterministic digital twins just doesn't make sense. We can piece all these bits and pieces together, but then if you present somebody with a digital twin that says, do X, and gives you no sense of the uncertainties, no sense of the confidence it might have in whether X is the right decision, whether it's safe, it's going to be hopeless. So we have to be incorporating uncertainty in the physical world, our inability to measure certain things directly, or the noise that come with sensors, but also our uncertainty in the digital world. The fact that we are going to be using models that may be imperfect. In many cases, we might be using surrogate models, reduced order models, so uncertainty in every aspect of our digital world. This is where the probabilistic graphical model comes in. Everything in our digital twin, our states, our control, our decisions, our data is represented as a random variable, and those entities are the nodes in a probabilistic graphical model. And again, the edges in a probabilistic graphical model represent relationships. Now, because everything is represented as a random variables, those relationships are conditional probabilities. So uncertainty really baked in for every step of the way. I'm not going to talk about it in detail today because I want to spend time talking about the educational work, but our past work, and I think I may have spoken about this last year or the year before at Multicore World. But our past work has really developed this idea of the probabilistic graphical model for the predictive layer of the digital twin, where we've shown how you could take this structural digital twin for an unmanned aerial vehicle and map all the different aspects of your data, models, and decisions into a structured probabilistic graphical model. And then once you've built this graph here, the tasks of data assimilation to update the models as the aircraft structural health changes, that just sits on top of the graph structure here. The task of determining optimal actions, so for example, the task of doing mission replanning in the face of changing structural health, again, just sits here on top of the graph. So again, I'm not going to talk in detail about that, but that's work that we have done in the past. Let me maybe skip over that. All right, so that brings me to the second part of the talk, where I want to show you how we're taking some of these ideas. And by the way, maybe I haven't said it explicitly, but I think one of the incredible powers of thinking about a digital twin in this graphical way is that it's going to let us have a common abstraction, a common sort of mathematical foundation for digital twins of vastly, vastly different systems. And in what I've shown so far, I've given a couple of examples of this aircraft structural digital twin. And now I'm going to talk about a digital twin of an educational system. These could not be more different, right? The aircraft structural digital twin, what sits at the core of the digital twin is a finite element model of the linear elasticity equations that tell me, given these material properties of the wing and given these loading conditions, here's what you might expect to see in terms of stresses and strains on the wing. So it's a very physics-centric approach to the digital twin. We don't have any conservation of mass, momentum, and energy in the education system, sadly. So here what you're going to see is an incredibly unstructured, complex system where we have data but no physics. And hopefully by the end of the talk, I will have convinced you that the graphical model, this way of thinking about the digital twin as a graph, actually has this role in these two very disparate examples, and I think pretty much everything in between. So the work I'm going to show you is the work of my PhD student, Luann. Luann's actually been working with me for many years. She's right now in her final year of finishing her PhD in the computer science department at UT Austin. And I've just got some of the papers that we've co-authored together. I'm going to talk mostly about the work in these first two conference papers that are shown here. But over the years, we've done some other work together, including using a graphical model to look at the impact of the COVID disruptions on mathematics education at the elementary school level in the US, which was both interesting and also quite distressing. All right, so educational digital twin, you saw flashed up there the different elements of the probabilistic graphical model for the aircraft, where I had things like material properties, it's interested in computing things like strains and stresses. Just because the educational setting doesn't have governing equations does not mean that you can't go through a process of a formal mathematical extraction of the system. So that's exactly what we do. We think about the state of the system. What are the things that we want to be able to track? Things like student enrollment, student engagement, student outcomes, demographics, course enrollment, success rates, institutional resources, faculty capacity, so everything you could imagine wanting to track. We think about control inputs. In the aircraft, control inputs are the control surfaces that you can deflect on a wing. Here, the control inputs are the changes that you can make, the changes you can affect in the physical world. You can make changes to curricula, to the way you advise students. You can have interventions like tutoring interventions. You can add resources. Thinking about all the different kinds of observational data, I actually shouldn't make jokes about these things. I was going to say we don't yet have students instrumented with sensors, but if Elon Musk has his way, maybe we will. But we have, of course, grades, attendance records, assessment results, institutional records, engagement analytics. So many disparate kinds of observational data coming in many different shapes and forms, owned by different people, and with different temporal scales and resolutions. On the, and I shouldn't make these jokes because Nicholas is recording this and I might get whisked away somewhere by the, anyway. I suppose I could always just move back to New Zealand, right? Yeah, yeah. On the digital side of things, you know, again, we want to think about how we want to represent this incredibly complex system via our models. I already said a couple times, we don't have conservation of mass, momentum, and energy, but we will be using empirical and machine learning-based models to represent the system, thinking about how you measure rewards or performance, costs and benefits, and then the quantities of interest, things that we might want to be able to predict about the system. What I'm going to show you today, the work that we've been doing with the Texas Higher Education Coordinating Board has been focused on educational pathways, and you know, it's just an example here. What does it mean for an educational pathway? So say off the bat, we've been looking at community college students in the US, and so I actually don't know if New Zealand has an equivalent so much anymore. I guess a little bit with some of the universities that were technical institutes in the beginning. But in the US system, many students start off in community colleges because, in large part, because it is a much more economically feasible way to start their education in terms of cost. And of course, the cost of higher education is a huge, huge issue for many, many people. And so in community colleges, they can earn associate degrees, but for many students, it's start off in community colleges, do the first couple years in community college with the intent to transfer into a 4-year institution like UT Austin, to then complete a 4-year bachelor's degree, but having done so at reduced cost in the first 2 years. So this idea of transfer students is, I think, incredibly important for a broader swath of the population to have access to high quality higher education. But it turns out that and I'd say the states have worked really hard to try to make these transfer pathways feasible, sort of having clear guidelines about what classes it would take to be able to transfer in, what classes will count for credit in the school, like for example in UT Austin, really trying to put in place a lot of guidelines to facilitate success. But when you start to look at the data, it is so depressing because you see just what the outcomes are. And these are, in many cases, students who are coming from economically disadvantaged backgrounds in the first place. Many of them are working full-time jobs at the same time as they're in community college. And they are taking classes, often the math classes are gateway classes where they will fail, pay and fail, pay to take them again and fail. And ultimately, the transfer success rates are not even close to what you would hope for an education system that really serves the population. So these are some of the questions that we are trying to look at with the idea of a digital twin, recognizing that these academic trajectories are nonlinear, multifaceted, and time-dependent. By the way, just like things on aircraft, and this is why I love it, because this is a dynamical system. It's a complex dynamical system. And just, you know, as an example, we have one here. Jennifer enrolls in a community college for the first time. There are readiness requirements in reading, writing, and math, and you'll see those popping up in our graphs. She enrolls in these classes. The other thing I should say, the scale at which the community colleges operate, not only are many of the students working full-time, many of the faculty have full-time jobs doing other things and teach part-time. And so the one-on-one student-faculty advising for what courses to take just often is not there at the scale that's needed. She takes these classes, she fails college algebra, she doesn't enroll. And this is something that's called stop out, which is something that's defined when students do not enroll, but then they come back later on. And you see in this notional, everything I'm going to show you is notional in this example. So she could be dropping out at this point. It actually turns out to be something called stop out, where she actually re-enrolls in spring 2016, takes more classes, passes, and then this is one where there's a successful transfer. So this is the kind of pathway that we are looking to model. And again, just to draw out what some of the challenges are here. We are talking, and now we're just talking about Texas. Right? Texas is a big state, but it's one state of many. Millions of students, hundreds of public post-secondary institutions, and so you can just imagine the scale of what we're talking about here. The variety, the different kinds of data, the grade reports, if you buy me a drink, I can tell you some of the stories about the way this data, I mean, you can probably imagine the way that the data are stored. The velocity, so the dynamic nature, the frequency with which some of this data are collected, and the changes that occur, all the questions about the veracity, so you have all the V's of big data here. But of course, the value in being able to navigate this kind of dynamic data, and I probably don't have to convince you of just what value you could bring as you think about these complex pathways if we could support interventions at the student level, but also give guidance to decision makers at the institutional and state levels. And then the variability. What's shown here, so I'm not showing you any real data at all today, and actually everything that's on the screen you could find online. So these are the standard reports that the Texas Higher Education Coordinating Board uses, and so the structure of these reports is online. But as you can kind of guess from the images that are shown here, these things are all tables. These are all tables of the student, right, their gender, are they economically disadvantaged, what degree are they in, what major are they in, right, all these tables, and there are many, 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 many different sort of tables in these different reports. So we got asked to do this project actually by the person who was the Commissioner of Higher Education in the state of Texas at the time. And so the question is, could we start to bring modern modeling and modern computing to start to kick off even an evolution in the educational system? So we came into this with this idea that the way to represent the system is as a graph. So again, just like in the aircraft example, start to think about a knowledge graph and an ontology. You have courses, you have institutions. And by the way, I put this up here on the screen. This took probably a year of trying to figure out how do you even abstract the system? What should the nodes in the graph be? What's a node? What's a relationship? I think is actually fascinating problem. But you can see here kind of where we landed, right? We have courses, course attempts, students, academic readiness, awards earned, majors, semesters. All of these things are entities in our knowledge graph. And they are related by edges. So a student might attempt a course, a student might enroll in a given institution or might take a particular enrollment action at a given institution. By the way, some of these community college students are actually enrolled in multiple institutions simultaneously. So you have to construct a graph that emits these kinds of things. So we define an ontology. And then, again, just like in the aircraft example, here's an instantiation, just an illustrative one. And in the way that I've shown this example, there's the student at the middle of it, and the student is attempting different courses. We're endowing the edges with properties where we could start to think about endowing grades on the edges. Of course, you could also have grades represented as nodes. Different classes, different institutions here, Austin Community College and the University of Texas at Austin. So you get the idea of how we go about trying to structure this vast, complex system via the knowledge graph on the base level of this multi-layered representation of the digital twin. So this one doesn't look as good if, oh, actually you did close the blinds, so it probably looks a little better than it was when I did this morning. But the things I'm going to show you, and by the way, I can't show you any actual educational results. I can only show you stuff about the graphs. But the things that I will show you is a graph where we have 7 majors. So, right, biology, business, I can't remember all the ones that are in there. So 7 majors and 6 cohorts. So these are students from 2012 to 2020. So it's a tiny, tiny fraction. And this is in Texas, tiny, tiny fraction of actually the whole thing. Already that knowledge graph is 15 million nodes and about 40 million edges. So of course there's a lot going on. Okay, I don't want to go into the details, but one of the incredible things about once you have taken this complex system and represented it as a graph, you now can reach up on the shelf and grab all the incredible things that you can do with graphs, right? And things like selection, projection, and aggregation. And you can now take all those questions that you might want to ask of the educational system and turn them into operations on the graph. And what's been particularly challenging, and one of the reasons the Commissioner asked us to get involved in this, is that these pathways involve behavior over time. And when you have tables, and you have tables for each year, and all these different tables, trying to trace out pathways in student behavior, the dynamic nature of the system is practically impossible, And so now representing this as a graph where the time element, the dynamic element of it is kind of baked into the way we structured the graph, lets us now, like I said, reach off the shelf for all the scalable graph operations to be asking questions like, you know, can I, so define selection of vertices and edges with logical predicates. Find me all the students across the state of Texas who took these two classes together and then failed college algebra. You know, those kinds of questions, which they really just could not answer those kinds of questions before we came in and started doing this graph modeling. Okay, keep an eye on the time. All right, so there's the knowledge graph, right? That's the bottom layer of the digital twin, and remember the predictive layer is the probabilistic graphical model. So again, I probably don't need to go into too much detail. Just like in the aircraft example where we're representing everything as random variables, in the aircraft example we are using, we're formulating things as a Bayesian inverse problem, we're solving optimal control under uncertainty problems with the physics models. Here we don't have the physics models, so we are using all the tools of AI and machine learning where we are learning, in this case, posterior distributions. One of the big challenges we have is how to make all this tractable. And so there are a whole lot of sort of assumptions and simplifications that have to go in there. I distilled this down. I had a whole slide on this, but I distilled it down to just two, actually it might be coming on the next slide, 2 bullet points. But there's a whole lot of domain knowledge that you can bring to this problem. For example, there are prerequisites that are defined. And so even though students do sometimes take classes out of order, for the most part, right, you can't take Calculus 2 until you've taken Calculus 1. So there's a lot you know about the graph going into it. I think if I go on the next slide. And so what we are doing as we are building up the probabilistic graphical model, and remember we're trying to also build this probabilistic graphical model over all these time steps so that we're capturing the dynamic behavior. We are using a combination of expert knowledge and also learning the structure of the graph from data. And some of the tests that Loen has been doing actually is to look and see how some of the state-of-the-art methods for learning the graph structure itself from data compare to what we actually know as experts in terms of where there are and are not links in the graph. But even just getting the topology of the graph is really a huge challenge. Okay, so once we've been able to do that, I don't know how well this is rendering towards the back, but this is an example of the kinds of things we can do. We can also operate transformations on the graph to, like I said, ask and answer particular questions in the educational setting. One of the things that was of a lot of interest to the coordinating board was what are the sequences of classes that are maybe indicators or predictors of whether a student is going to drop out, stop out, or have a successful transfer? Because I think they recognize the complexity of the system is not that it's just, oh, you can see college algebra as this real barrier for many students. And by the way, maybe I don't need to say this, but just to contrast, right, college algebra, for a child growing up in a privileged household like mine, many of those kids are taking that class in middle school, not even having to take it in high school. And we're talking about a population of people who have to take college algebra in their post-secondary education. And so it has been years for many of them since they had the basic math. And it just breaks my heart, as somebody who loves algebra, breaks my heart to see that this is the kind of thing that stands between this population, successfully getting into a degree, and sometimes algebra maybe is not even that essential. So many questions about that. It's not just one class, but could you start, and what these little triangles are showing here is we have, in this visualization, all the different classes that are taken across different semesters. I think this is just for one of the majors. The size of the node there and the links show classes that are commonly taken together. And then, I don't know if you can see them, they're maybe not rendering too well, but the little lines showing here are showing you those sequences that have high prevalence of causing dropout, stopout, or successful transfer. And so then you can start to ask the question, you know, what is it about these sequence of classes as an institutional leader? Is this a place where I can start thinking about bringing additional resources, or even thinking about curriculum redesign, or about advising students, you know, don't take these 2 classes in the same semester, because we're aware that there seems to be, of course, correlations, not necessarily causation. So these are the kinds of analysis. Second to last slide, I want to say a little bit about scalability. I also want to give a big shout out to Dan. Again, if you want to sort of hear a funny but heartbreaking story, I don't know, Dan, I don't know how long it took us. It felt like years. It was probably the first 6 months of the project to convince them that, first of all, tech could be trusted to take the data sets, because there's a thing called an education research center, which are kind of the owners of all the educational data. But the only way you could access the data was in logging in through a web browser. And so you had to log in through this web browser, and then people would use R or whatever they were doing to do their analysis. And we said, you know, we were under contract to do this project. It's like, we're going to need more than just like a web browser. We need access to the data. So we went through this whole process and actually ended up being allowed to host the data in a secure enclave at TAC. I think we're the first researchers ever in Texas to be able to do that, which was remarkable. So Dan and his TAC team were really amazing. And again, it's funny, but also heartbreaking. For a while there, Loen was coding. It's the equivalent of, I don't know, coding with a blindfold on and a lag of 3 days, where she would type the code, send it to somebody at the ERC, he would compile it and then run it on the data set, and then 3 days later write back to her, oh, it gave this error. And then she would fix the error, and then she would send it back to again. So luckily, after about 6 months, we were able to move on from that. But this is just sort of a sign of where the educational community is in terms of the way they think about their data and are able to actually interact with it. So some of the things we showed is, you know, how scalable is this? Loen did comparisons against the traditional table-based methods. And the big conclusion is, in read queries, as you might expect, orders of magnitude faster. And in fact, you know, this query here, this query about pathways, very quickly when you start to look at pathways that go over multiple semesters, the table-based methods just can't even begin to do it. But where you see that we're much more expensive are any of the write queries. And so what does this mean? This means if you get a new semester of data, of course it's much faster to just like say, oh, here's another table, here's another file, whereas we have to actually go in and add the new data to the graph. If there have been changes, it might even involve a change to the architecture of the graph. So more time-consuming for the write, but this is where this idea of a digital twin that you're really updating and letting it follow along with the real world, with that bidirectional interaction is so important. Okay, so last slide. Again, just to summarize, digital twins are kind of everywhere. One of the things that makes me quite sad is that I don't feel that anybody will pick up creating a digital twin of education unless they can make money off it. And it's not clear that there is money to be made off this. So I was very grateful for the opportunity to have this commissioner-directed project to be able to work on these things. And what we really did was proof of concept at a relatively small scale. You saw the 6 cohorts, the 7 majors across the state of Texas. This is a tiny, tiny, tiny slice of what is possible in terms of the outcomes that could be improved for education, actually, I think, across the world. If we as a community could start to, first of all, help the education community get their data into a form where it could be queried and managed at scale, and then, like I said, you don't have to invent new techniques to do analytics on a graph. The finance industry has done that for us. So let's think about how we manage the data and the digital twin paradigm for all of that. Just in terms of some of the limitations and some of the future directions, of course, privacy restrictions and sharing is a huge, huge issue here. And so what we've been doing has been entirely walled off. You know, even the question of what should be shared with the student themselves, it's their data, but the questions of who owns the data and who could have access to it, could you give access to advisors, These are really, really tricky questions, and of course these are questions that show up in digital twin applications of other areas. We talked a little bit about the data and the data sovereignty issues. So of course many of these, as we start to talk about social data like education. The culture change and the adoption is a really huge one. I would love to see education sort of come into the modern age of computing, and I just think there's so many benefits. In terms of future directions, maybe back to a little bit more of the technical part of it, one of the other really powerful things about these graph models is that I think they give us a really good mathematical foundation to actually start tackling some of these tricky questions about security and privacy. So another piece of Luen's thesis, she's actually shown how you can take the probabilistic graphical model representation, turn it into a finite state machine, and then connect it with the formal verification methods. And so this is now going to the question of verification of a digital twin. So maybe let's forget about education, come back to the aircraft example. How could I verify that no matter what went on with a sensor failing or strange things happening on board the aircraft, that I could verify that my digital twin will always result in some kind of a safe behavior? So those formal methods exist in the community. They're used for verifying flight control systems. Again, this probabilistic graphical model representation of a digital twin gives us a way to connect to those methods and to information theoretic approaches that start to ask questions like, if I have this digital twin and I pass this information from the physical to the virtual and an adversary would intercept that information, what would they be able to infer about my physical system through the interception? So another sort of plug for the graph-based approaches is that they really are a window into incredibly powerful techniques that I think could be a way for us to ask and answer some of the tricky questions about security and privacy of digital twins. And then on the education, if we have the chance to, would again like to extend that. So that is it. I finished as promised in about 40 minutes. I'll be happy to take some questions and hear any comments. So thank you.